To find the distance between any 2 points on the Cartesian plane, all we need to know about is Pythagoras' theorem, and it's really quite simple. Now, if you plot your 2 points, even if it's just a simple graph and not even to scale, it can be a lot easier to see what to do. So basically we want to find this distance here, and the way that we do it, we can draw up a right angled triangle, either coming across this way, or the way I prefer to do it is take the higher point and drop a line down until you become straight across from the other point, so that you've made yourself a little right angled triangle like that. Once you've done that, it's quite easy to see how long each of these sides are. So here we've got the point 7, 4, so it's the height up here is 4 and the height of this point down here is 1, so it's quite easy to see that this one is 3 units. And along the base here we're going from the point 2, 1, which lines up with the 2, along to the point 7, 4. So the x values of 2 and 7 tell me that this length is 5. Now, we already know from Pythagoras that a squared plus b squared equals c squared, where c always has to be the hypotenuse, or the long side. And when you're finding the distance between 2 points, that long side will always be the distance that you're trying to find. So what we can do here is just sub in the values that we know. We know 3 squared plus 5 squared will need to equal our distance squared. Simplifying this, we have 9 plus 25 equals c squared, and 25 plus 9 is 34. So if I know that c squared is 34, then c must be the square root of 34, which I can put in my calculator and find, or leave my answer as a surd, whatever they've asked in the question. I know that this is a little bit less than 6 because the square root of 36 would be 6, and this is just a little bit smaller than that. At that point, look at your answer and think, a little bit less than 6, would that sort of fit with my picture? And yeah, that makes sense. If this is 5, this would be a little bit more than 5, maybe not quite 6, so it seems like I've done the right thing. If you've made a mistake, it'll be quite obvious because the answer you get here really just won't match up with your picture. Now in this module, they're trying to teach you a way to do it where you actually use a formula, so that instead of doing this method, dropping down the line and making your triangle and working it out using Pythagoras, they want you to come up with a formula that will work every time. Now, what I want you to think of here is, well, how did we actually find our 3? If truth be known, we found our 3 by taking 4 and subtracting 1. That gave us 3 because this was up level with 4 and this was level with 1. So what we really did here is we took our y values and we did y, let's say y1 minus y2. If we call this one, let's call this x1, y1, and we could call this pair x2, y2. We took one of them away from the other, and then we squared it. And then what did we do to get this 5? Well, we actually found the 5 by doing 7 minus 2, didn't we? And so we have a plus here, because that's what we have in Pythagoras' theorem, and we found that by taking one x value away from the other. Okay, and what we ended up then with is our c squared. Now to get to the end, what did we do? If we wanted to come up with a formula that would come out straight away here with the c, let's let those not join up. We knew that once we had an expression for c squared, the way to find c is just to find the square root of all of that. So really I could improve my formula here by unsquaring the c so it's just a c, and putting a square root bracket over that whole thing. And that's now a pretty reasonable expression for c. It might be even nicer to write it with c equals, so it looks like a recipe for how to find c if you have any x's and y's. Now, there's nothing wrong with the way we've written this here, but what would have happened if we'd labelled our x1 and y1 and x2 and y2 round the other way? Well, let's just think about that. If we did 4 minus 1 to get our 3, what would have happened if we'd done 1 minus 4? Well, 1 minus 4 would have just given us minus 3. And what would happen when we square that? Well, squaring minus 3 gives you the exact same thing as squaring 3. So you can see why it really doesn't matter which of these y's you call y1 and y2, as long as you're consistently using the same one and subtracting it from the other one. So if you've called these, if you've started with doing 4 minus 1, then you'll need to also do 7 minus 2. But they can really all be be mixed up, and you can see that the sign isn't going to affect anything because we're squaring it anyway. Now when you see this formula written, it's often written around like this: y2 minus y1, x2 minus x1. Again, it would make no difference. I just happened to label this with the 1, so I figured we'd use what we had to explain how we work things out here. But either way around, it's really the same formula. So if we wanted to do another example now and work it out not using any picture whatsoever, we could basically just use this formula to find our distance. Let's say we want to find the distance between minus 4, 2 and 3, 1. Without even graphing these, I can throw them into this formula. Let's have a go. C equals square root of. Now, let's call this one x1, y1, and this x2, y2. All we need to do is y2 minus y1, so that'll be 1 minus 2, and square it, and then add it to x2 minus x1, that's 3 minus minus 4. Now 3 minus minus 4 is actually 3 plus 4. So I'll write that in, I can do that part in my head. And now we can figure out what we've got. 1 minus 2 is minus 1, and when you square minus 1 you get 1. And 3 plus 4 is 7, squared is 49. So C must be the square root of 50, which is not an exact whole number. It's going to be 7 and a bit because the square root of 49 is 7. Now another way you might see the formula, if you're adding two things together, it really doesn't make any difference which order you add them in. So it would be equally valid to write your formula doing the x's first and then the y's. Now, why am I showing you variations of the formula? Because a different textbook might write it a different way, and it's good to understand that they're all really doing the same thing. Now, memorising a formula is fantastic, because if you can memorise this, then when you're given some points, all you need to do is chuck them into the formula and the answer drops out. But we need to understand where the formula comes from, so that if you were stuck and you got this same question and you couldn't remember the formula, or you just weren't sure whether you needed to subtract things or add them, and you're feeling a bit confused, you could always just draw this. Even if it's a rough sketch, minus 4, 2 could be here, and 3, 1 can be over here. You're finding this here, so it's a nice flat little triangle. We've dropped a box down and straight across and made a right angle here. Now, how tall is our triangle? Well, this is 1, and that one is 2, so it's only one tall. And how wide is it? Well, we're going across here to minus 4, and this way we're coming across to 3, so it's 7. So drawing that triangle a little bit bigger so I can see what I'm doing, I can say that c squared is equal to 1 squared plus 7 squared. Away you go with your Pythagoras. 1 plus 49, c squared equals 50, so c must be the square root of 50. And we've got the exact same answer. Which way is better to go? Well, as long as you know Pythagoras' theorem, that's your backup, and you've always got that to fall back on. You know how to graph things, so this is really quite straightforward. Memorising the formula is fantastic because it makes it nice and easy, but this is also a good fallback, and it's good to know both methods.